Welcome students, and congratulations on making it this far. We've learned a little bit about derivatives. I know that this is all material that you've covered in your calculus class, but it's still very helpful to review it to make sure that we are all on the same page by the time we start our fluid mechanics class. Now let's talk about applications. Probably one of the most important derivatives you're going to use in fluid mechanics is the acceleration. The acceleration of a fluid particle is essentially the change of its velocity with respect to time. But first, let's talk a little bit about how we define velocity when it comes to fluid mechanics. You see, in fluid mechanics, we will sometimes study velocity as a function of position and time, which means that if we have a fluid particle moving in a three-dimensional Cartesian space, then the velocity will be a function of its position, which is determined by the variables x, y, and z. And it will also be a function of time. Because velocity has both magnitude and direction, it is a vector. And you'll find that it's very typical for a Cartesian velocity vector to be defined by the terms u, v, and w, where u represents the x component of the velocity, v represents the y component of the velocity, and w represents the z component of the velocity. So in this case, our velocity vector, u, v, w, is a function of x, y, z, and t. But we also know that the position of a fluid particle also changes with respect to time, which means that x, y, and z will all be functions of time. Now, with all this information given, what's the acceleration of a fluid particle? In other words, what is the derivative of velocity with respect to time? Remember that here we're talking about a total change, not a partial change. Well, we can find this by applying the chain rule. So let's see what that gives us. The chain rule tells us that dv over dt will equal dou v over dou x, that's the partial derivative of velocity with respect to the first variable, times dx over dt, that is the derivative of the first variable with respect to time, plus dou v over dou y times dy over dt, plus dou v over dou z times dz over dt, and finally dou v over dou t times dt over dt. Using the chain rule, we've been able to find the acceleration of a fluid particle. However, you can note some things here. Note that dx over dt, the change in the x position of the fluid particle with respect to time, is simply the x component of the velocity. dy over dt is simply the y component of velocity. And dz over dt is simply the z component of the velocity. Now this gives us a much more commonly used form of the acceleration equation, where dv over dt equals u times dou v dou t plus v times dou v dou y plus w times dou v dou z plus dou v dou t. For this type of derivative, we typically write the d in capital letters, and it takes the name of the material derivative. Now we're not going to go into details in this video, but when you are taking your fluid mechanics course, you will learn a little bit more about what the material derivative is and where it comes from. But notice that all you need to know is just some basic concepts in derivatives and the chain rule. And with just that information, you are able to find the acceleration of a fluid particle.